Regarding lenses, there are two types of lenses. One is called convex lens, other is called concave lens. Convex lens is thicker in middle and thinner at the edges, while concave lens is thinnest at middle and thicker at edges. In other words, we can say that lenses are made up of prism. So as prism deviate light, lens may deviate light. At prism disperse light, lens may disperse light. So the property of prism and properties of lenses, they are alike because lenses can be formed by prism. How? Convex lens, suppose it is a sphere and it is another sphere, and these are the overlapping part. So if I take this part as a lens, so if this is my lens, then it has this surface and this surface as a refracting surface. Radius of this surface is same as radius of this sphere. So suppose its radius is r1. So first surface have radius r1 and this sphere has a radius r2. So second refracting surface of this lens has radius r2. Now if I draw this lens here, it looks like this. This is called convex lens. And this is first refracting surface whose radius is r1, and this is second refracting surface whose radius is r2. Now see, this is one piece of the lens, this is another piece. So this kind of pieces, when kept over each other, we get a lens. This is another prism, this is inverted prism, this is inverted prism. Prism may be like this. This is also a prism. This is also a prism. And its prism angle, if you want to find, you have to extend these two refracting surfaces, and you have to take angle between these two refracting surfaces as prism angle. So this is also a prism. So if I take one prism like this, one prism like this, one prism again like this, and one prism like this, and put one over other, and we get this convex lens. So you can say that this convex lens is made up of large number of prisms. So property of prism is also present in this lens. This is called convex lens, and this surface is called first refracting surface. This surface is called second refracting surface. Similarly, and this is sphere 1 and this is sphere 2, and I put a glass material here. So this is first refracting surface, its radius is this, radius of this sphere, let it be r1, and this is second refracting surface and its radius is radius of this sphere, r2. So this lens, which is thin in middle while thick at edges, this is called concave lens. It is thinnest here and thickest here. Like this. So this is concave lens. It's also made up of large number of prism. So property of this lens is same as property of these prism. This is first refracting surface, this is second refracting surface. Now generally we take object on left side, this side. Generally we take object on this side, image on this side. Object on this side, image on this side. Generally we take like this. So the incident ray will be like this, and distance is measured from center. This is called optical center. So if you have to measure object distance, you have to go like this. Or if you want to measure radius of this surface, center of this surface is somewhere here, so you have to go in this way. So radius of this surface will be negative. So in case of convex lens R2, radius of second surface is taken to be negative. While if you want to measure radius of this surface, so center of this sphere will be somewhere here. So you have to go in this direction, in the direction of incident ray, to measure radius R1. That's why R1 is taken to be positive. So in case of convex lens, R1 is taken to be positive and R2 is taken to be negative. So remember these things. While in case of concave lens, R1 is to be measured in this direction, R2 is to be measured in this direction. So R1 is taken as negative and R2 is taken as positive. So in case of concave lens, we take R1 as negative, R2 as positive. In case of convex lens, we take R1 as positive, R2 as negative. Now in any lens, suppose this is a lens, convex lens, then this length between this edge and this edge, this length is called aperture of lens. Aperture. So if I take this as x, this as y, then distance between x and y is said to be aperture. So aperture is xy, distance between x and y. Generally we denote it by d, small d. So this is called aperture. Now you know, optical axis, you know, this is first surface whose radius is r1 and center is c1, suppose somewhere here, and this is second surface whose radius is r2 and center is somewhere here, c2. So a line connecting the centers of the two spheres, this line is called principal axis for this lens. So this is principal axis. This is principal axis. And the center of lens through which this principal axis passes, this is called optical center. Optical center. We denote it by C or O. So this is optical center, and C2, C1, this is principal axis. Principal axis. So aperture, principal axis, optical center, you know. Now important thing, if lens is thin, then ray that is passing through optical center goes undeviated. But this is true only if lens is thin. So the light which passes through optical center goes undeviated in case of thin lens. So if lens is thin, then any ray that is going through optical center will go undeviated, go straight for thin lens. Same is for concave lens. Suppose this is a concave lens. This is first surface, so center of first surface will be somewhere here. This is second refracting surface, center of second refracting surface will be somewhere here. If you connect these two center by a line, this is called principal axis. and center of lens at principal axis. This is called optical center O. And let this point be x, this point be y, and this xy distance between x and y is called optical center. So you must be clear in terms aperture, principal axis, optical center of lens. In this case also, if a ray passing through optical center, it goes undeviated. Any ray that passes through optical center goes undeviated, provided the lens is thin lens. So this is also true. So remember these terms related with lens. Now how name of lens is given. You know, there are two surfaces, first surface, second surface, and both has got different radius. Both surfaces are convex. So this lens is said to be convexo-convex. First surface is convex, so for first surface convexo. Second surface is also convex, so convex. Convexo-convex. Convexo-convex. Now whether name of first surface you have to write here or second surface you have to write, that is decided by whose radius is large. So if radius is large, first surface has more radius, then name of first surface you have to write first, and then name of second surface. For example, if I take a lens like this, so this surface has got finite radius, this surface has got infinite radius. So this surface has larger radius, so we have to write name of this surface first and then name of this surface. And this surface is plane, so we write plano-convex. So this lens is plano-convex. Whether it is kept like this or it is kept like this, no change in name. Because again I have to write first name of surface which has got larger radius. So plane surface has more radius, this surface has less radius, so plano-convex. So this is also plano-convex, this is plano-convex. Now if I take this surface is concave and this surface is convex, so you know radius of this surface is lesser than radius of this surface. So by seeing you can say that R2 is greater than R1. So we have to write name of this surface first, then name of this surface, and this is concave surface, so this is concavo-convex lens. So this lens is concavo-convex lens. Similarly, if I take lens like this, this surface has larger radius, this surface has lesser radius, this is convex, this is concave, so larger radius has first name, so it is convexo-concave. So this lens is convexo-concave. So name of this lens is convexo-concave. Similarly, if I have a lens like this, this has larger radius, this has lesser radius, so I have to write name of this surface first, so it is plano and then concave. So in that way name of lens is written. Now focal length for thin lens is given by lens maker's formula. So I am going to derive lens maker's formula, and remember this, that this formula is valid only for thin lenses. So it is lens maker's formula. Lens maker's formula. Lens maker's formula. Suppose this is convex surface, refractive index mu 2 mu 1, and if I take an object somewhere here, a light is incident on this surface, a light that goes like this, it falls on the surface normally, so it will go straight. So the ray which is going along principal axis, that pass without any deviation. Let this point be P1, pole for first refracting surface. This point be A. So this is incident ray. Now mu 2 is greater than mu 1. Mu 1 is air, mu 2 is glass. Suppose if I draw normal here, it is like this. So you know that light is going from rarer to denser medium, so it will bend towards normal. So let this goes like this. So this is refractor ray. Now if mu 2 is continuous in this side, then this ray will go, this real ray will go along this path and will meet this real ray which is coming along principal axis, and both will meet here. So here there will be image formed by first refracting surface. I1 will be image formed by this first refracting surface only if this side medium is having refractive index mu 2, means this medium is continuous, so that there is no any more refraction. So refraction due to this surface, image is formed here if there is no any other refraction. But in case of lens it is not so. In case of lens, there is another surface here, there is another surface here, and this ray is coming up to here. After that this ray going to enter in other medium, so there will be one more refraction here, so image will not be formed there, because image of this refraction will be I1, but I1 will be present only if there is no other refraction, but here there will be one more refraction, so image will not be there. Image will be there only if refraction at A occurs, no other refraction, and no other refraction only will occur if there is continuous medium mu 2 present up to there. But here mu 2 is limited in this region. Here air is present, mu 1 is present. So there will be one more refraction here. Now if I draw a normal here, suppose this is normal here, and light is going from denser to rarer, so it will go away from normal. So the real ray will not follow this line, will go like this and will meet this real ray coming along principal axis somewhere here. So actual image will be formed here. So this is actual image formed, and this is P2, pole of this refracting surface. Now if I take center of this lens as O, optical center, and this distance I am taking as T, thickness of the lens I am taking T. So distance between these 2 points will be T by 2, right? Now if I consider a refraction through first surface only, then this will be object distance for the first surface, and image of first surface. If there is no second refraction, then image of first surface will be here, means from here to here. This is image distance for first surface. Right? But if there is one more refraction here, then for this surface you may take, this is incident ray, so converging incident ray is there. It means we have to consider virtual image, so we have to consider the point where this ray, incident ray on this surface converges. That point is supposed to be object for this surface, and we know that this ray is going to converge at this point. So I1 behave like object for second refracting surface. I1 behaves like object for second refracting surface. So let us write refraction at first surface. Refraction at first surface. So we have derived already formula. Refraction is taking place from rarer to denser. So we have to use formula mu2 upon V. Now V for first refracting surface is V1. So V1 minus mu1 upon U. U is this. And then equal to mu2 minus mu1 upon R1. R1 first refracting surface. Right? This is equation 1. But image will be formed at I1 only if mu2 medium continues up to I1. Otherwise final image will not be at I1. Now I1 behaves like object for second refracting surface because there will be a second refraction here. So I1 image of first refracting surface. Image of first refracting surface, though there is no I1 there, behaves like object for second refracting surface. Right? Now, what is object distance for second refracting surface? For second refracting surface, object distance will be measured from P2. So it will be V1 minus T. V1 minus T. So a refraction at second refracting surface. Here refraction is taking place, light is going from denser to rarer medium, so you have to write formula like this: mu1 upon V. V for this surface is this. This is distance of final image. So it is mu1 upon V minus mu2 upon U. Object distance for this surface is V1 minus T, because V1 is distance from P1, but I need object distance from P2. So it is V1 minus T. equal to mu1 minus mu2 upon R2. So this is refraction through second refracting surface, equation 2. Now if lens is thin, then P1, P2 and O all will be very near to each other. So for thin lenses, distance P1O is also equal to, let it be C. Distance between P1O is also equal to distance between CO for thin lens. So these approximations we have to consider. So for thin lens, P1, C, P2 are very close to each other, and so we can write OP1 approximately equal to OC, and that is U. Similarly, P1 I1 is nearly equal to CI1, this distance. So distance from here or distance from here or distance from here we can take as V. So it is P2 I1 and that is equal to V1. So this is very small, so all these distances we can write it. It means at place of V1 minus T, we approximately can write V1 because T is very negligible. So here V1 minus T can be replaced as V1. And then final image P2I. P2I is V and P2I can be approximately written as CI. P2I is equal to CI is equal to V. So these approximations we can make. So after making this approximation, we come to know that this is approximately equal to V1. So we can rewrite is mu1 upon V minus mu2 upon V1 is equal to mu1 minus mu2 upon R2. So let this be equation 2. This be equation 2. Now adding equation 1 and 2. Adding equation 1 and 2. Mu2 upon V1 minus mu1 upon U plus mu1 upon V minus mu2 upon V1 is equal to mu2 minus mu1 upon R1 plus mu1 minus mu2 upon R2. This we can write after adding equation 1 and 2. We can write it like this. Now see, this and this get cancelled. So it is mu1 1 upon V minus 1 upon U is, if I take minus common here, I can write it minus mu2 minus mu1, and then I can take common mu2 minus mu1. So here will be 1 by R1 and this side becomes negative 1 upon R2. So 1 upon V minus 1 upon U is equal to mu 2 upon mu 1 minus 1 upon R1 minus 1 upon R2. So this is formula, lens maker's formula, and we know that 1 upon V minus 1 upon U is 1 upon F, thin lens formula. So it is mu 2 upon mu 1 minus 1 into 1 upon R1 minus 1 upon R2. So this is formula for thin lens, lens maker's formula. So this is lens maker's formula and it is for thin lens. Now mu 2 is refractive index of lens material. Here mu 2 is refractive index of lens material, and mu 1 is refractive index of surrounding medium, in which lens is kept. We may write mu 2 upon mu 1 as mu 2 1, means refractive index of lens material with respect to surrounding medium. This is refractive index of lens material with respect to surrounding medium. So we may write mu 1 2 here minus 1. So this is lens maker's formula and it is valid for thin lenses only. For thick lens it is not valid.